All right, this video, or this series of videos, is going to be a little bit different from normal. I am going to take an old BC Calculus test. This is one, it would be usually the first unit in the BC specific stuff where you learn new integration techniques that you didn't learn in AB. With what I do, it's chapter 7. So we get into integration by parts, partial fractions, improper integrals. They are integrals that involve infinity. We'll just kind of scroll through all these here. We get into Hopital's rule that are beyond just what you do in AB stuff. And then you get into logistic growth models, which is what this one is right here. So what we're going to do is go through problem by problem, and I'll do as many as I can in a video, and hopefully include some timestamps for you and some links to other videos in the descriptions. So let's start with this. Oh, one other thing I should say. These yellow highlighted ones, this is an old test, but the yellow highlighted ones are ones that I changed for other reasons. So the solutions are just going to look a little bit different. Not too much to worry about there. All right, so first one, integral from 10 to infinity of 9 over x minus 8 dx. All right, so there it is right here. What we do is we integrate this thing, and I use limit notation. I have to use limit notation anytime I have an infinity. Typically we do an A or a B, A for the lower bound, B for the upper bound. So you can see here infinity is the upper bound, so I go to the limit as B goes to infinity. And what I did here was I integrated this thing right here. 9 over x minus 8 integrates to this. And then I wrote my evaluate bar. And then I'd go and I just like plug in the B as if it was a number, but I keep my limit notation. So the B is the upper bound. That means it goes first. 9 ln of B minus 8 minus 9 ln of 10 minus 8. I'm not even going to worry about this right here. I'm just going to look at this over here. You can see that I've got the limit as, I've got the interior, this B, going to infinity, right? And then I subtract 8. It's still going to be infinity. And that makes me take the ln of infinity, which, as I said here, that goes to infinity. So what do I say that this integral does? It diverges because it goes to infinity. All right, question 2 here. Integral of x cubed e to the 2x dx. Let me pop down to the solution set. Okay, the scan's a little bit grainy here, but we're going to roll with it. I'm definitely using integration by parts. It's called tabular method. I dir one term and I int the other. In this case, I got x cubed e to the 2x. I know the x cubed is going to derive away, go to 0 eventually, so I put that on the dir side. Dir all the way down until I get to 0. And then I integrate the right side. Notice the right side has an e to the 2x, so I get a half there, right? So each layer of integration, I get another multiplier by a half. So that's where I get a half, a quarter, an eighth, and a 16th. Then I do my diagonal arrows. I don't need to escape in this one like I do in some others. And I alternate plus, minus, until we get down to the end. And then we multiply along those arrows. For the way that I wrote my solution here, I decided, hey, they all have e to the 2x's in them. So I'm going to factor that e to the 2x out to make it a little bit easier to write everything. Notice x cubed over 2 is this times the half. Minus comes from the alternating arrows. 3x squared over 4 is this times that. And so on as we go down. Hopefully that one's good. Let's go to the next one. Okay, letter C here. Integral from 1 to 9 of 3 over the cubed root of x minus 1 dx. So here, I used limit notation. Pretty sure in this one it's actually not totally necessary once we get to this integral step. The reason I err on the side of using that limit notation is because if I try to plug 1 into the integral here, or into the thing that we're integrating, I get a 0 in the denominator. And that's typically when we want to use limit notation. So what do we do here? I integrate cubed root of x minus 1. That gives me x minus 1 to the 2/3. Remember, so one really common error here is to get the 1/3 power here, because that's the way square root works when I have it in the bottom. But it's 2/3 because if you think about a number line, if we're at a negative, if this was a vertical number line and we're at 0 was here, negative 1/3 was here, to go up a full unit, I would land at 2/3 in the positives. And that's because of how negative numbers work. Anyway, in power rule, we go up by 1 unit when we do our power rule. So that's why I got the 2/3. This 3 is that 3. This 3/2 is dividing by 2/3, which we do when we do power rule. So you should be okay with all this stuff. And then I'm going to evaluate that from from 1 to 9. So what do I have here? I have 9 halves. You may say, yo, where'd the 4 come from? Well, that comes from plugging in 9 to x right here. That gives me 8 to the 2/3 power. When I do 8 to the 2/3 power, I cube root 8, which gives me which gives me 2, and then the 2 up here says to square it. So that's how I get that 4. You should be okay with that. That's something we do a lot. And then when I plug in 1, I get 0. So I just get 4 minus 0 times 9 halves, which does come out to be 18. All right, let's scroll over to the next one. We're just going to use this one, this part of the document for now. All right. So, for this one, it's the integral of x times ln of x squared dx. So, I didn't label it here super well, but here's my dir side, and here's my int side. You may say, how'd you decide those? Well, whenever I have an ln, I typically want to put that ln on the dir side of my integration by parts. Why do we do that? We do that because I know how to take the derivative of ln. I do not have the integral of ln memorized because we have to use an integration by parts for it. That's not my expectation for you. I should add that it is common for us to also have ln integrals that are u-subbable. So you should always look for some u-sub first before we try to do integration by parts. The other thing that I'll say about this is that this 2 can move out front using the plug rule if we want, and it makes it a little bit easier. All right, so let me go through the details. So this x is on the int side. This part, ln of x squared, is on the dir side. You may say, why did you get 2 over x squared, or 2 over x? Well, I get a 2x for my chain rule divided by 1 over of, and the of is x squared. Those cancel out to give me 2 over x. I think it's actually easier to plug it and then take the derivative and get 2 over x, whatever works for you. Then, on my int side, this x is that x. Integrate, I get 1/2 x squared. So, you should know, bam, it looks like I can escape here. So, I'm going to do this product. That is 1/2 x squared, that's this piece, times ln of x squared, that's this piece, minus the integral. Remember, when we go back, we escape. 2 over x is this. 1/2 x cubed, or x squared, sorry, is this right here. And then this all simplifies. The 2 and the 2 cancel. I don't have all this work shown here. And then the x divides into there to give me, remember this is a squared, not a cubed, to give me an x, right? So if I integrate that, I get 1/2 x squared again. And this negative is from that negative. So hopefully you're good with that. Let's roll on to the next one. Okay. All right. Another improper integral. How do we know it's an improper integral? Well, there's that infinity right there staring me in the face. So whenever we see these infinities, we always need to use limit notation. I can't do arithmetic on infinities. So this is the integral from 2 to infinity of 1 over x to the 5th dx. So the first thing I'm going to do is anywhere there's an infinity, I'm going to use limit notation. Since it's the upper bound, I use a b. Standard practice, but you don't have to do it that way. And then this is power rule on the 1 over x to the 5th. Remember, 1 over x to the 5th is a negative exponent. So I go up 1. That gives me to x to the 4th. It's still in the bottom because it's x to the negative 4th. And I divide by the new power. So I've got the negative from dividing by a negative 4. That's why the 4 is in the bottom. So this is a quick jump from here to here. Let me talk about this term first. So this term is 2 plugged into that. Okay, that gives me 2 to the 4th. Times 4, you may be like, wait. This is negative. Why is that positive? Well, this is the lower bound, the 2, so we subtract it from the other one. So that's why I get positive there, because there's a double negative. It's minus this negative piece. All right, now let's talk about this 0. This 0 comes from the b limit part of this thing. I get the limit as b goes to infinity of this thing. So the infinity is sort of being plugged into this. That gives me 1 over 4 times infinity to the 4th, or at least we can think about it that way. So what is that? Well, that's still an infinitely large number in the bottom of the fraction. Well, when I get that, the fraction itself goes to 0, and that's why we have limits. So 0 plus this thing. And then if you do 2 to the 4th times 4, you might have to use your fingers. That's okay. You're going to get 1 over 64. All right, I think we got time for one more. I'm going to save this one for the next video. So we'll stop here. I'll see you in the next one. Bye.